So the best performing algorithm
is 6 because it's a constant.
All right, so we're going to write it on the bottom. All right, so we're saying 6 is the best performing algorithm. All right, anyone disputes that? No. All right.
No.
Good. So you don't have to put them all in just one order. You can tell me the worst and the best as well, and we just keep working. So which one you say is the worst?
The factorial, n factorial.
N factorial. Oops. All right, so n factorial. Got you. All right. Okay. So far, so good. All right. So we have ruled out 2 out of the 15. Okay. When we get to the n cube, what did you notice there? How many? Was it only one function had that behavior?
No, sir.
No, sir.
Cubic? No, sir.
No, because when we sum them, like in the case of n minus n squared, plus 5 times n cubed, what we do is that we are saying that this algorithm, when it sum all of this, the worst behavior is going to be, the worst behavior here is going to be, the worst behavior here is going to be n cubed, because n squared is worse than n squared. So even though we sum them up, the worst behavior, so this algorithm, no matter how we sum them up, we only look for the worst term to say that this algorithm that we're looking at here is actually equal to, it's equal to the order of n cubed. You see? So based on what I've just said here, based on what I've just said here, cube plus log n. So the other one that we have here is, we have one called n cube, and we have another one called n cube plus log n. So all these, this one, and this one, they are all the same. So therefore, we'll just write those on the same line. Got it?
Sir, question. All right, so you're grouping them all together, but wouldn't one be running better than the other one?
As n
Since there are
increases,
more things to the algorithm?
No, as the size of n increases, as n tends to infinity, these terms are minuscule compared to this. So this is the term that is going to dictate the worst performing behavior of the algorithm. This is the term that is going to dictate the worst performing behavior, and this one as well. So therefore, when we say, when we have a summation, it is the worst term in the summation that dictates the behavior of the algorithm.
Sir, so when they're like that, the order doesn't matter in which you place them?
It doesn't matter which order you put them in. So what we're saying is that in this case, they fall between 6 and n factorial. So I'm just going to write them out in one line, right?
So no matter how the summation is, the worst one always dictates where it will fall between factorial and 6.
Exactly.
All right, sir.
All right, so for these three, they behave similarly, these three. Because you see, this could be a program where one part of the program is behaving like this and another part of the program is behaving like this. So when you sum the amount of work done, this is the worst part. So it's the same thing that is happening here. All right, so I'm just going to write them out so somewhere here. So one is n minus n squared plus 5 times n cubed. All right, so that's one. Another one is n cubed. And the third one is n cubed plus log n. Okay. All right, so we have 3 and 2, 5 of them so far. So we still have 10 to put to place. Next, we know that n squared behave what? Better than this line.
Cubic, yes, sir.
Yeah.
So how many terms do we have with n squared? Only one? Yep. Right, so n squared is going to be somewhere down here. Come on. All right. Okay. Then going closer to the 6 now. Which of these functions would be the better performing algorithms?
The log of log n?
Okay.
Okay, we have the log of log n, right? Because the log of log n is a smaller function than log n.
Oh.
So the log of log n. Then?
And then it will be followed by log n
Log n.
Yeah, I don't see anything smaller than log n.
And we have above it, we have log n. Uh-huh.
Square root of n, sir.
Huh?
Square root of n.
All right, do we have any log terms? Any other log terms?
You have log n squared. Well, log n all squared, but I'm not sure about that one.
N log n also, sir.
All right, n log n is worse than n.
What about log n all squared or log n squared? I don't know how to say that one.
All right, so we have the root of n, and we have log n squared. So log n, log of n squared. So log of n squared right here. All right, so right inside here, oops. We're going to insert it right in here. So that's log of n squared. Mm-hmm.
And then the root of n, the square root of n.
Then the root of n
I want to ask though, what makes log n squared the better performer than the square root of n?
Okay, what?
Between those two last ones, what makes one the better performing algorithm than the other? Okay.
All right. For you to do this, I would suggest that you put in some numbers. Use some numbers to test the growth from 0 to 10,000. Okay?
Yes, sir.
All right. All right, then closer to n factorial, we'd have had what? 2 to the n Is there a difference between 2 to the n and 2 to the n minus 1? You see, 2 to the n is equal to a constant times 2 to the n minus 1, don't it?
Yes, sir.
So therefore, this behavior, both of these would be the same.
So,
Okay. Then the next one below that would be 3 over 2. Hello?
So you're saying 2 to the n is the same as 2 to the n minus 1?
Yes, because 2 to the n is a constant. 2 multiplied by 2 to the n minus 1, just as we did for n cube, and 5n cube is the same order, right?
Sir, so you're basically focusing on 2 to the n.
So it's basically they are roughly the same order of growth because it's a constant factor. This one is just a constant factor of this.
So they're both.
So they would behave similarly. The order of growth would be approximately the same. Okay? All right, what else we have? The next one is 3 over 2 is equal to 1.5 raised to the n. And 1.5 raised to the n is smaller than 2 raised to the n. So that one would go right here. 3 over 2. Come on. Raised to the n.
Sir,
Mm-hmm.
wouldn't that be in the same line as 2 to the n?
No, because this is a smaller base. The factor 3 over 2. So what I want you to do for me is to draw the graph and look at the graph that you get when you draw them. So visually you will see how they perform. So the steeper the graph is, the worse the behavior. Okay. What do we still have to put in there? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 2 more. Which are they? N log n?
N log
And
n.
n.
All right. And n.
And n.
All right. So right
Hello?
here, we're going to insert it between here and here. So in terms of order, what will happen is that n log n will be worse than n. All right, so going from the worst to the best performer, it would be n factorial being the worst, then the exponential, 2 to the n and 2 to the n minus 1, then 3 over 2 to the n, then the cubic, then the squared, then the logarithmic, then the linear, then the square root, the log square, the log, because these really, this log n and this log square, they are very close in terms of their performance, but I want you to draw them to see if they actually fall in the same line or if one come above the other. This one, the log n and the log n squared. And log n definitely is better than log n, and 6 would be the best performing algorithm.